That's San Pablo, a small village about 2 miles high in the Guatemalan mountains on the Mexican border. Let's take a look at energy flows in the world. Who has the energy? It becomes very evident if we look at a picture of the Earth with each country at nighttime. Who has the energy? Where there's light, there's energy use, there's wealth. The United States uses about a quarter of the global energy. What does that mean? Well, there are about 7 billion people in the world. 300 million in the United States, and a tenth of that in California. That means about 5% of the world's population is in the United States, and about 0.5% in California. So on average, the United States uses 5 times as much energy per person as the world average, or more than 6 times people who are not in the United States. We can go to World Mapper and get an idea of a lot of different things. I encourage you to go. We can look at world population. So here the size of the country is proportional to the population. You see the United States rather small compared to India, or even Japan is big. Australia, very few people live in Australia. Now we go and look at energy. And who's fat, dumb, and happy here? And Africa looking very emaciated. Japan actually looking rather large. Very high energy use. And we look at energy again, the world's largest traded commodity, with food number 2. Although food should really be added on some level to energy, because food is energy. We remember seeing this, the energy stocks and flows from the Earth, or for the Earth. And we recall that the world's population uses about 17 terawatts now, it's updated. And we get from the sun, it claims 162,000 terawatts. Is it possible? Let's do a simple calculation. On the Earth's surface, under full sunlight, we get about 1,000 watts per square meter. So how much energy or how much power does the whole Earth get on average depends on the surface area of the Earth. What is the surface area of the Earth? Well, this is your planet. We should know, right? And it shouldn't be hard because the length of a meter was defined as 10,000 kilometers is from the equator to the North Pole along the prime meridian. So the circumference of the Earth, or 2 pi r, must be equal to 40,000 kilometers, yielding about 6,400 kilometers for the radius of the Earth. Similarly, the metric system has defined a volume and also a mass. So 1 liter is defined as 10 centimeters by 10 centimeters by 10 centimeters, a perfect cube. And a liter of water is defined as 1 kilogram. So the density of water is 1 kilogram per liter by definition, or 1,000 kilograms per cubic meter. Prove that to yourself. That's 1 ton per cubic meter. So what is the total rate of power coming to the Earth from the sun? Please calculate that and verify that it is approximately 162,000 terawatts. The Joule experiment was very important in providing a way to compare mechanical energy, that is the energy released as these weights fell a certain distance, mgh, to thermal energy. How much this fall increased the temperature of the water. So we can compare then joules to calories and show that 1 calorie is 4.19 joules. Similarly, this allowed us to compare chemical energy to mechanical and thermal energy, because we could take chemical energy and burn it and heat the water, providing this comparison. If an apple falls off a table, it's about a joule. That's potential energy, gravitational potential energy, mgh. However, cooling an apple, the thermal energy required is considerably more, about 1,000 joules. And in eating an apple, what it provides for your body is about a megajoule, 1,000,000 joules, and that's the chemical potential energy of all the sugars that can be burned in your body. So we can look at energy, work, and heat. All the same unit. A joule is a Newton meter. Work is force times distance, so this makes sense. Potential energy is what you get if you do work on an object lifting it against gravity. Mass times gravity times height. You can measure the energy something has by heating something up with it. For instance, if we heat water, the amount of heat provided the water is the mass of the water times the specific heat of water times the change in temperature. This is how we define the calorie, the energy needed to heat 1 gram of water, 1 degree Celsius. Or for English, the British thermal unit, which turns out to be 1,055 joules. Okay, so power is the rate of work, or the rate of energy conversion. So power is work divided by time. Now be careful, right? Because a watt is a unit of power, is a joule per second. This is a watt down here. This is work, or joules, up here. So the rate at which you heat something could be a British thermal unit per hour, a BTU per hour, if you're working with English units. Or a horsepower, which is about 3/4 of a kilowatt, 746 watts, is our unit of mechanical energy, the English unit of mechanical energy, for cars, for instance. The most interesting unit of power I've run across is the ton. This is the rate at which heat is absorbed by an air conditioner. It's 12,000 British thermal units per hour. And what is this? This comes from the days when you would cool your house or your building with 1 ton of ice. So you'd have 1 ton of ice per day would provide you with 12,000 BTU per hour. A little bit of history. So these are the stocks, how much energy I have, and these are the flows, the rate at which energy is converted, or your power. So we can turn this around. If power is work divided by time, work, which is energy, which is heat, is power times time. And so a joule is also a watt second. Prove that to yourself, please. Now, when we work with electricity, for instance, a joule is very small, and a watt second would be a tiny amount of electricity. So we use kilowatt hours, which is 1,000 watts for an hour, or 1,000 watts times 3,600 seconds. So if you use a 1,000 watt hairdryer for 1 hour, you've used 1 kilowatt hour of electricity, which will cost you about 15 cents. So the stock of energy that you have might be the size of a battery that's charged, or the amount of gasoline in your tank. The flows, how fast you can convert that energy, is not determined by the amount of gasoline you have, but by the size of the engine, by the size of the electric motor, or the wattage of the light bulb that you might have. Other units that are interesting are the dietary calorie, how many calories are in a candy bar, which is 1,000 thermal calories, or 4,190 joules. We can measure energy in terms of gallons of gas, or barrels of crude oil, or tons of oil. You often see tons of oil equivalent. It's not someone's toe, it's the amount of energy in 1 ton of oil. And then we have these prefixes in the metric system. A kilo is 10 to the 3rd, a mega is 10 to the 6th, giga 10 to the 9th, but we've got a lot more. A trillion, terawatt, for instance, is 10 to the 12th. Peta is quadrillion. A petawatt is 10 to the 15th. Or exajoule. For instance, in the United States, we use about 100 exajoules a year, or 10 to the 20 joules per year is our rate of energy use. There you go.